Today we have the main topic of our course because our course is related to the measurement of solar cells, and the main characteristic of solar cell is IV curve. So, how to measure IV curve? First, it seems to be quite simple. You have a source of the light which has any required condition. I mean, we have a spectrum which corresponds to IM1.5 G or any standard spectrum. We have intensity of this light which is calibrated using a reference solar cell. Then we can produce required temperature. So we have our solar cell. It's like a diode here in this equivalent circuit. Then we can think to measure voltage which is dropped on this solar cell, and using some standard source, power source, we can apply some voltage and measure the current. So I just want to remind that almost any current measurement, an electrical current measurement, it's a measurement of the voltage drop, this shunt resistance. So I mean, in the most cases of precise electrical measurements, it's just a voltage drop when you know the resistance of this shunt resistor. Okay, it seems to be quite easy, but actually it's not so easy as it could be. If you have a look to this equivalent circuit, so we can see for the dark measurements. Actually, for the dark measurements, it's nice. So we can produce our solar cell by some load resistance in the dark. I mean, the value of this resistance depends on the voltage, but it could be some passive, some passive you know. But the problem that it's only for the dark measurements. I mean, if you apply some positive voltage, you can measure this positive current without any problem when you use some power source. So you see, it's no problem. But when you try to measure the solar cell under light, things is different. Because in this case, our solar cell corresponds to another power source. I mean, we can think in terms of internal resistance and electromotive force. I mean, it's like for any power source. If you have a look to some specification, normally you can find the maximum current, voltage and power, but physically this power, it means the internal resistance. For the solar cell, we have one source. For the power source, it's another one, and the problem is that the current direction is different. We have some kind of contradiction, because for the solar cell at the positive voltage, I mean it's the same voltage, we have a different current direction. So it's a negative current, it's a direct voltage. So it means that we have some kind of competition between two power sources. And if you want to know precisely the voltage which would be in this circuit. Actually, we have to solve this. So we can to refer to this equation, which depends on the VOC. So actually, electromotive force for solar cell, it's a VOC voltage, and then internal resistance of the solar cell and of the source, of the power supply. And actually, so for the power supply, the internal resistance corresponds to its power. So I mean, the higher power you have, the lower resistance you have. Concerning the solar cell, actually it corresponds to mainly not to the efficiency, because the difference in efficiency is so few times of magnitude. I mean, if you have a bad solar cell with a 5% of efficiency and a very nice solar cell with a 25% of efficiency, it's only a factor of 5. But this internal resistance corresponds mainly to the difference in the area of the solar cell, because the area you can scale it in a few orders of magnitude. It could be only 1 square centimeter, or for 5 by 5 it's 25 square centimeter, or 10 by 10 it's already 100 square centimeter. So I mean, the difference in the area could be very significant, and actually this internal resistance would be very low. So I mean, if you have a very low power resistance, I mean, it's equivalent to high power or large area solar cell. In this case, the voltage of your IV curve would be equal to some value which is near to the VOC. I mean, it's like you have a stronger power source of a solar cell and smaller source of power for power supply. You can try to here move to zero. So you set the zero value at this power supply, but you won't go to this point. But your solar cell doesn't allow you to go to this point, and you are here near to VOC. So it's some kind of problem which also actually could be solved if you use a quite powerful power supply, but there is no reason to do it, because it's a little bit crazy. Try to fight against the solar cell. The simplest solution to measure sorry, it doesn't work. I don't know why. Sorry for this delay. Okay, I'll use some problem with yeah, it does work on the screen, but I will try to reset again. So I will try to close and open again. Yeah. So the simplest solution first is to use controlled load. So it's like some variable resistance, and it could be in the simplest case just some variable resistance. You can change this value, and you can sweep along IV curve. but it could be more complicated device controlled by a computer and with high load power up to 100 or even few hundred watt. So this is one of the solution how to measure the IV curve in this quadrant, fourth quadrant. But the problem that you are limited by the two cases, by the VOC and short circuit current, and in some specific cases you may be interested go further, because for example if you have some kind of a knee here, you don't know exactly what does it mean. I mean, if you have some strange behavior just near to the VOC, and sometimes you may be required to go further. And the same if you have something here which is not maybe normal behavior like this, and some kind of knee of IV curve, and in this case it's quite important to go further to the reverse bias. For these cases it's better to use a special source meters. The main idea is that you have two separate channels. One is to control the current, and another to measure the voltage. So it's actually the main idea of this source meters for measurement and the fourth quadrant. So in this case you can easily go up to positive current and negative voltage without any problem, and get more information. And another point, so another problem which is more practical problem, when you try simply to measure the IV curve of a solar cell using 2 points, which seems to be the reasonable way. So for example, if you have a solar cell like this, you can use one tip on the top and some conductive table to have a contact with the back contact of a solar cell. Or maybe for a different design you can be required to use two tips. So the diameter of the tip could be quite small, so you can get some resistance here, or in case of some oxide layer, for example here at the top, it's at the bottom contact of the solar cell. In this case you can get some contact resistance, which is not really related to the solar cell, to the internal properties of the solar cell. It's just related to your measurement circuit. So I mean, I'm speaking about the contact resistance between the measured tip and the contact, the metallic contact of the solar cell. It's nothing to do with using some internal properties. It's just some kind of artifact resistance. It could be even resistance of the wires. For example, if you have a tip with a small diameter of the wires, or if you have a large area of the solar cell, in this case you can get a problem of the contact resistance. So in this simplest case, even if you try to use nice source meter with the different channels of the current and voltage, if you have a look to the equivalent circuit, you can see you have some contact resistance. So when we pass the current through the solar cell, we have a current here, and you have a voltage drop, this contact resistance. which could be actually quite stronger. So if you remember, when we tried to calculate solar cell with for 1 square centimeter area, so I mean when we try to calculate this, the current density, so it means it was related to the current divided to the 1 square centimeter. The contact resistance of 1 ohm could lead to approximately 1% of efficiency loss. So if we are thinking about a large area solar cell of 100 square centimeters, this contact resistance could lead to a huge error of the measurements. It's and it is not related to the properties of the solar cell. It's just related to the problem of the measurement. So to avoid this problem, there is a quite seamless way. Is to use the 4-point measurements. Sometimes it's called a Kelvin probe. The main idea is to separate two channels of the current and the voltage measurement, not only in the source matter, but also in this when you contact to the solar cell. So you have to use 4 separate contacts which are not connected between each other. They are connected only via the contact of the solar cell. So you have no connection here. You have only connection via this some contact, some metallization, some. And the same as another part of, I mean, for example, it could be a bottom contact, it could be another contact. And you have 2 separate circuits. The first circuit is a circuit of the current measurement. So if we have a look to the equivalent circuit, we can see that we are in series. And as you know, in the stereo connection, the current is equal for each element. So you should not care about this voltage drop because you just measure the current. So the current which flows through the solar cell is equal to the current you have measured. So there is no problem for the current measurement. And concerning the voltage, you have a separated circuit. In this case, even you have some contact resistance, the internal resistance of voltage meter, so your voltmeter, is should be quite large enough. So there are a lot of years ago it was maybe a problem to find this kind of device, but now it's quite simple. Even the cheapest device have a very significant internal resistance, and in this case you can actually neglect the current which is in this circuit, and it means if your current is almost equal to 0, so it means that you have almost equal to 0 voltage drop for this contact resistance. So the main idea that in these 2 separated circuits you have a measurement of the voltage which is correct, because the internal voltage of the voltmeter is quite high. So in this case you have almost no current, so almost no voltage drop. And here in the current circuit you have a series connection, and the current is always the same for your ampere meter and the solar cell. So it's a nice way to avoid any problem with the contact resistance. But you should be careful for this kind of measurement using 4-point measurement connection, because normally, so people want to measure IV curve when you prepare your program or you use another software already prepared. Normally you set the voltage value, and then the source meter it try to find the condition which corresponds to this voltage, and actually it try to pass some current. So in principle it's okay, it's nice, it's quite easy, so you don't care about the real voltage of this ampere of this source of the current, and so you just fix the pairs of the value of the current and value of the voltage. But in case if you lost the contact, so you have no contact here, so it means that you have no feedback for this device, and if you want to set some, for example, 0.5 or even less, 0.1 voltage, device would apply some current here, have a current. Actually, it applies some voltage to provide the current, and because there is no feedback, it sees it's zero. It try to increase this voltage. It try to increase. There is zero, and you can get the case when this value of voltage or current is too high, and you can even broke your samples, so you can kill the device if you lose this feedback. So the first thing you have to think about limits. I mean, when you try to put some program for the measurement, normally this kind of source meter it allows you to put some limit value of the current and of voltage, so don't forget about it. But there is another thing which is more, let's say, advantage of this 4-point measurements principle, that actually there is a quite simple way to avoid this problem. I mean, to avoid the problem of the broken contact. You can simply check this the resistance between two contacts. So we can disconnect, for example, from a source meter and check the resistance between two contacts. And if you have some reasonable value which corresponds that you have a real contact, some few ohms or even 100 ohms, it means that you are connected. So in this case, you are sure that there is no problem. I mean, for the both pairs, for this and for this one. And there is no problem with the contact you can measure, is the first advantage. And the second, that actually for 2 points measurement, you have no option to check if you have a contact or no. Actually, there is only one way, it's to reproduce this 4-point case. I mean, if you have some independent connection, for example, for this contact, and measure the resistance between them. There is no other, so we can do it manually, but in any case, you would reproduce this circuit. I mean, the connection. And sometimes, for this kind of connection, you can get a real problem how to get contact. For example, if you have a aluminum BSF contact when aluminum is a little bit oxidized, and it's not so easy to get good contact between this back contact and the measurement table. So you have to manipulate with the sample, and actually you are not sure that you have really nice contact between them, or maybe you have some another problem. In this case, using this principle of the separate contacts, you can be sure that you have a contact between this and this. For example, you just simply measure it. So it's another advantage. So concerning the correct IV curve measurement, first of all, it's quite say convenient to use the 4 terminal to save your time, because you can check if there is no problem with the contacts first, and the second, which is really important, that there is it's only one way to avoid any problem of the contact resistance. I mean, in this case, you can measure without any doubt about contact resistance. And just some values to realize that if you are in the milliampere would say range, you should care about this contact resistance. I mean, of course it depends on the value, but normally for say some average solar cells, milliampere current, it's already the value when you have to think about the contact resistance, because the zero resistance could be very significant. Actually, the same thing for the DAC measurement. I mean, the same. If you want to make some correct DAC measurement, you have to avoid any contact resistance if you want to analyze some transport properties, etc. So, okay. So now we know that we have to use 4-point measurement, but if you want to place for example, 2 tips on the top side of the solar cell with a design like this, for example, so we can ask the question where to place the probes. So, for example, 2 limited cases. If you put 2 points near to each other, it's in the one place, or you can separate them by diagonal using this and this point. And actually, in case of any, would say, problem with this sheet resistance, with some spreading problem, you can get the difference between them. So for this case, you would measure something like this. For this case, you would measure this one. And actually, it's some kind of example for heterojunction solar cell with the ITO top layer and metallic grid. So I mean, it could be real. The case is the difference in the field factor, and the question, which measurement is correct? Actually, so I would say, on the one hand, it's quite the answer is quite simple, because there is a strong requirement how to place the tips. On the other hand, it's not so easy. But so the first idea is that actually it's something which there is some strong requirement that you have to place your tips close as possible, as close, and in the places where you are going to connect the terminals. So if you model design predicts that you have to connect here your bus bar, so you have to locate the tips in this point. If you have, for example, 2 or 3 bus bars, you have to use the same number of the pairs. So I mean, for example, for one bus bar, if you have one connecting point, so you have one pair. If you have a 2 bus bar with 2 connecting point for the future model design, you have to use 2 pairs, and for 3 pairs, etc. But you have, what does that mean? 2 pairs. It means that you have 2 contacts here, so two, for example, tips which are really near to each other, but not connected, only via the grid, and another pair, and the tip for the voltage measurement is connected to another tip for the voltage measurement. The tip for the current measurement is connected to another. Not the cross connection, I mean, you cannot connect a tip for the current measurement with the tip for the voltage measurement. It's, in this case, you are not in a four wire measurement condition, so it would be two wire. And so it seems to be quite simple, quite strict. But actually, it's simple and clear if you are thinking, if you already know about your model design. If you are thinking about in some industrial scale or industrial, I mean, if you know that your cell cells, they are designed to place to the model, and you know exactly where you will contact them to connect with another one wafer with another wafer, etc. But if you just in some scientific, some laboratory level, so you have some kind of flexibility. So you can imagine it. You can say, okay, I will connect here and here. I will have 2 terminals. So you are a little bit free, but so there is some reason, because in this case you can at least estimate the potential of your structure. I mean, if you have this kind of the case, I mean, for this measurement you have a IV curve like this, like blue line. For the 2 separated points you have a IV curve like this. So it means that you have losses, but the losses, they are really related to some series resistance, but actually the series resistance is related to the spreading. I mean, that it's not enough. So you have to, you know what to do if you want to really connect this point, or you can just say, okay, I will connect this and this point separately. I mean, 2 bus bar, and so it's another way. So, but what's important that if you are thinking about the model design, if you know already how to connect, so of course you have to locate your probes at the places of the contact connection. Second point, so if we already provide anything concerning the light source, so we have a spectrum and we have irradiance, then we have to think about the cell temperature. So there are different ways to control the temperature of the solar cell, but in most cases you are working in some room condition. I mean, you and the measurement devices. So it means that Normally, if you are at some room temperature, it means that when you illuminate your solar cell by this 1 kilowatt per square meter, in this it would lead to heating of the solar cell. So it means that normally you have to cool the solar cell, and there are different ways for the cooling. So first, to use something like a fan, similar the process of the computer, but it's quite difficult to control the temperature precisely, because actually we really need the precise control of the solar cell temperature. There are two another ways, using water cooling and using a Peltier model. So another thing that we have to think about, thermal contact between the solar cell and this cooling plate. I mean, have some table, cooling table, and you have to think about good thermal contact, and in the most cases also electrical contact. So for this reason, normally you have to think about vacuum clamping. So here is some example how to realize it. So we have a table which is which has a conductive place, and actually it's a 4-terminal plate. I mean, have two tips for the top contact, and you cannot see, but there is another tip in the center which is isolated to connect to the back contact and this surface. So you have 4 contacts. Then you can see some holes for the vacuum clamping, and you can control the temperature of this table. For example, using the chiller, so it's kind of water cooling. The advantage that in this case you can provide really high power, I mean high dissipation power, so you can cool it. There's a really high area. I mean, heights I think is relative, but if you are thinking about 30 by 30 centimeters, so you can use in this case some. It would be rather better to use some water cooling with power, high power. And another advantage that it's more or less inert. I mean, if you are thinking only about the standard condition at 25 degrees, so it's not so bad. Disadvantage that so you know, any liquid cooling system, you have some unfortunately some chance that you have a chance of a leakage. So if you have some water or any other liquid, so you see if you have a leakage, so it's not really nice for your devices. Another approach is to use Peltier models. Advantage is flexible, so you can easily control the temperature in a wider range. Actually, the low temperature limit is related to the water vapor condition. I mean, if you have some condensation of the water, so normally you are limited at 10 or 12 degree from the low temperature, and for the high temperature, for example, for this system, you can heat up to 70 degrees without any problem. It depends on the power of your Peltier model supply. and requirement of the solar cell. But so you can, at least you can easy to get some fast measurement of the temperature dependence of your solar cell parameters. So again, you can imagine about some system which has some vacuum clamping and to provide 4-terminal measurement. This two plate of copper plates should be isolated. So then they are covered by a gold. Normally the tables for the solar cells, they are covered by some very conductive metals like a gold. And of course you need to use some radiator because Peltier module it has some cold and hot side, and to dissipate the energy from the hot side you have some radiator or maybe farm cooling. So some more or less conventional design of this type of system. Here is some design of the whole measurement system. So we have a solar simulator, it's clear, with the required spectrum. We have a measuring table which provides anything, I mean the electrical contact, the temperature, and vacuum clamping to get better electrical and thermal contact. So we have some solar cell and of course a reference cell. You can think about in situ control of the intensity, but this just in situ control of the intensity variation. It cannot be used to calibrate a system. To calibrate, you have to use only reference solar cell and then source matter. So if you have a look to some conventional set of the measurement setup, you already seen the solar simulator, this table, and for source matter normally it's a Kesley 2400 series. It's the most conventional way, I mean, to use this device. In some higher current condition, you can use some another Kepler device. But if you want to measure the model, of course the current is too high, and in this case normally you have to use some controllable load. And so you can collect this system yourself. You can buy or create a solar simulator, buy a device for the electrical measurement like a source meter, buy a reference solar cell and create some table, or you can buy everything already done. And quite often there is some software which is provided with these systems, and of course this software allows you to get information about the main parameters like VOC, short circuit current, fill factor, and maximum power. Now you can simply calculate the efficiency if you know the area, and actually it's only one parameter you need because the intensity you already calibrated your solar simulator using reference solar cell. But also in some softwares you can additionally get some values of the series and shunt resistance, It's similar that we try to calculate previously. But you have to realize that these values, which can be approximated from IV cube, they correspond to some values of the simplest equivalent circuit of the one diode equivalent circuit. I mean, it could correspond some series resistance, a shunt resistance. So you can get some ideas about them. I mean, that maybe have a problem with the contacts or problem with something, some other problem. But if you have a multi-junction solar cell or more complicated real equivalent circuit, you have to realize that maybe these values give you no information. I mean, it's always a question about this analysis of your results.